So let's continue looking at derivatives, and we're going to be kind of focusing on easier techniques of finding the derivative as opposed to maybe using the limit definition. So far we've learned the power rule, and we've learned the sum and difference rule, and the constant multiple rule. So let's take a look at some other rules, one of which is the product rule. And as you can imagine, we're going to use the product rule whenever we have essentially a product of two functions, so one function times another function. And so far we don't quite know how to actually find the derivative of something like that, so that's what we're going to want to look at. So let's say that we want to look at the derivative of, I'll put this in brackets, the derivative of a product. Now one might be tempted to say that, well, maybe we can just take the derivative of the first function and the derivative of the second function and just multiply them together. If you remember, that did actually work with limits. That is, there was a product law that if I took the limit of a function times another function, I could just take the limit of the first times the limit of the second. Let's kind of think about if that works for derivatives. So here's my proposition. I want to know if this is true. That is, the derivative of a product, is that just the product of the derivatives? So let's actually go ahead and pick a function f and a function g, just as an example, and kind of see if this formula works. So maybe we could pick f of x to be maybe x squared, and g of x to be maybe x cubed. And one of the reasons I'm picking power functions like this is, one, we already know how to take the derivative using the power rule, and two, if I multiply these two together, I know how to combine those just using some of our rules of exponents. Okay, so let's go ahead and come down here and see if this is going to work out for us. So I want the derivative of f of x times g of x. That would be the derivative of x squared times x cubed. And again, here was kind of what I wanted to look at. Can I just take the derivative of the first thing, derivative of x squared, times the derivative of x cubed? Well, let's see. So the derivative of x squared with respect to x is 2x. The derivative of x cubed with respect to x is 3x squared. And of course I'm using the power rule when I do that. And now I see that I can actually combine these two together. This is like an x to the first power. 2 times 3 is 6. X to the, and we add these exponents together. So that would be 6x to the third power. Now let's see if that actually, I'm going to keep doing this question mark here because I'm still not quite sure if we're doing this the right way. So let's take a look at this part right here. That is the derivative of x squared times x cubed. Well, I could have simplified that to begin with, couldn't I? I could have just brought the x squared and the x cubed together, and that would be x to the fifth power. And now I see I'm taking the derivative of x to the fifth. I can use the power rule. That's 5x to the fourth power. And I'm already seeing a bit of a problem here. Those two are not equal to each other. Okay? If this was true, I should get equivalent things because I started with x squared times x cubed. I brought those together using perfectly legitimate algebra, and I get a different derivative than this one here. So I'm kind of seeing then this is the correct answer. This one is not right. So unfortunately, it does not work that way. We can't just take the derivative of the first thing and multiply by the derivative of the second thing. Here's what the actual rule is. Okay, the product rule, again, if I take the derivative of two functions multiplied together, it is the first function, just by itself, no derivatives, times the derivative of the second function, that is the derivative of g, plus g times the derivative of f. So each one kind of gets its own turn for having the derivative taken. We multiply those together and then add them. Okay, so, and actually let's look at if I did prime notation. This is using Leibniz notation. Let's say that I did prime notation instead, just because I want to get familiar with all the different notations that we have. So using prime notation, the derivative would be f times g prime. So that would be f. This in prime notation is g prime of x. And then this in prime notation is f prime of x. Okay, so these two are the exact same rule. Okay, so you don't have to memorize both of these things. It's the exact same rule. It's just written using two different forms of notation that we've learned so far. So this one's going to be really important. We'll want to remember this. Okay. Now that we have what the actual product rule is, let's go ahead and try this again and see if we do come out to get 5x to the fourth. Okay. So I'm going to again try to take the derivative of x squared times x cubed. So using the product rule, I see that I have the first thing. So this is like my f of x function. And this is like the g of x function. So product rule says I just start with the first thing, just f of x. No derivatives, just that. And then I want to take the derivative of g. G is x cubed. Then I want g times the derivative of f, which is that. Now notice I haven't actually gone through and finished this yet. I need to finish by taking the derivatives. So I have x squared, derivative of this is 3x squared. X cubed, derivative of x squared is 2x. And let's do some simplification. So here I have, that would be 3x, add the powers, so to the fourth, plus 2x to the, again, add the powers, fourth, and here we go, like terms, 5x to the fourth, just like we had started out with. Now, of course, this isn't really a proof that the product rule works. I guess you could say it's a proof that it happens to work for x squared and x cubed. If you'd like to see a proof, your textbook likely has one, and you can also definitely find one online. Okay, let's go ahead and just try another example. Let's find the derivative of x squared times e to the x. Derivative of x squared times e to the x. Okay, so let's go ahead and use that product rule again. Now, one way that I like to write the product, or I guess say the product rule, is the first thing times the derivative of the second thing plus the second times the derivative of the first. So you'll hear me saying that quite a bit. So here we go. I have the first thing times the derivative of the second thing plus the second thing times the derivative of the first. So there's just my setup for the product rule. And now I can go ahead and take the derivatives. Derivative of e to the x is e to the x. And the derivative of x squared is 2x. Now we could go ahead and just leave it there. If you wanted to simplify a little bit, I do see that I have an e to the x in each term. So if you could pull the e to the x out and you'd be left with x squared plus 2x. Actually, I'm also seeing that I have an x in both terms, so you could pull an x out also. Any of these are perfectly legitimate answers. We've found the derivative. If we wanted to now, we could plug in a number, and that number would tell us what the slope of the tangent line is for that function at that particular point that we're plugging in. Okay. All right, so if there's a product rule, then you can probably assume that there's also a quotient rule, and there is. So I'm just going to go ahead and tell you what the quotient rule is. So let's start out with, if I have the quotient or division of two functions, and I want to look at the derivative of that, here's the rule. We take g of x times the derivative of f of x minus f of x times the derivative of g of x, all divided by g of x squared. This one's a little bit trickier to remember, but once you get some practice, it'll start to come a little bit more clearly, and you'll be able to remember it. Again, just for good measure, if I wanted to write this in prime notation, take the derivative, I'd have g of x times f prime of x, f of x, g prime of x, all over g of x squared. This one's just a little bit more condensed, a little bit easier to write. Okay, again, both of these are the quotient rule. It's just two different ways of writing it using the different notation that we've learned so far. Okay. Let's go ahead and verify this a little bit also. So let's pick two functions. Maybe the function x to the 7th for f, and maybe x cubed for g. Okay, so that means that I want to take the derivative of x to the 7th over x cubed. So I'll say prime. And let's see what we end up getting when we use the quotient rule. So it says I have the denominator first, no derivative, just the denominator as is. The derivative of the numerator. Okay, so I'm going to skip a few steps here because I think we're probably getting to the point where we can do the power rule in our head. So I want the derivative of x to the 7th. The derivative of x to the 7th is 7x to the 6th minus the top function, x to the 7th, times the derivative of the bottom. The derivative of x cubed is 3x squared, all divided by the bottom squared. Okay, so I just used the quotient rule to get here. Again, this was the derivative of x to the 7th. This was the derivative of x cubed. Let's do a little simplification. So let's see, I'd have 7x to the 3 plus 6, so to the 9th, minus 3x to the, add those, I get 9 also, all over x to the, we'd multiply these together, so that would be to the 6th power. And subtract these, again I can do that because these are like terms, they're both to the 9th power. So I have 4x to the 9th over x to the 6th, and when we divide we subtract the exponent, so I have 4x to the 3rd power. And notice that this simplifies to x to the 4th. The derivative of x to the 4th is 4x to the 3rd. So it's looking good. It's looking like that quotient rule works. So let's go ahead and do just one more example. So let's say we wanted to take the derivative of 3e to the x plus x minus 1 all over x cubed minus 2x squared. Okay, so we're going to take the derivative of this here. And again, the derivative gives the slope of the tangent line. That's kind of our main goal here in the end. We're getting the derivative as a function so that we would be able to find the slope of a tangent line at a particular point. Okay, so it looks like we're going to use the quotient rule, doesn't it? Because we have a quotient of two functions. So let's go ahead and do that. So the quotient rule says I have the bottom thing, the denominator. All right, no derivative yet. Times, and I'm going to go ahead and do the extra step on this one just because there's a lot more components going on. So I want the derivative of the top minus the top times the derivative of the bottom. Start to run out of room here, 2x squared. Okay, and I want that all over the bottom squared. Okay, so let's go ahead and take these derivatives. I have x cubed minus 2x squared, that was just the original denominator. Derivative of the numerator. Derivative of 3e to the x would be 3e to the x. Using the constant multiple rule there, that derivative of 3 times a function is 3 times the derivative of the function. So 3e to the x. The derivative of x is 1. The derivative of a constant is 0. So the derivative of this minus 1 would be 0. Minus 3e to the x plus x minus 1. Again, that was just the numerator. Derivative of the denominator is 3x squared, power rule, minus 4x. That would be the power rule and the constant multiple rule. All over denominator squared. Okay, now a lot of people would be really tempted to clean this up a little bit, but I don't really think that's all that necessary. We wanted to find the derivative, we found the derivative, it's right here. If we wanted to know the slope of the tangent line at some point, we could go ahead and plug that point in and then simplify from there. Okay, so that's the product and the quotient rule, and that'll be really handy for when we start looking at taking the derivatives of a little bit more complex functions like this.